El Nino periods may last for 3 or 4 to 7 years, and then the non-El Nino. So the equatorial Pacific goes from being warmer than normal to colder than normal, then warmer than normal, then colder than normal. Here again, 1998, much warmer than normal, then in through 2000, colder than normal. And then we had a period of warmer than colder. And so that is sort of the period of El Nino and non-El Nino years. The impact of an El Nino season is the warming of the equatorial waters of the Pacific Ocean, so the region actually south of Hawaii. And that warming of that equatorial water creates a much stronger, persistent jet stream moving across this part of the Pacific Ocean. And with the low pressure that sets up south of Alaska, it just produces a very, very wet and stormy pattern that moves across essentially the southern tier of the United States. This strong wind also moves all the way across the Gulf of Mexico and into the Atlantic Ocean, and during an El Nino year, this strong subtropical jet actually helps to reduce the number of hurricanes that form, or if hurricanes do form, it tends to deflect them out into the Atlantic Ocean quickly, that is, in the Atlantic Basin. All right, when we're talking about non-El Nino years, that La Nina I mentioned, but non-El Nino years, your more typical pattern is a large blocking high pressure area south of Alaska that causes the main storm track to be deflected way to the north. That keeps it much drier across the southern states and even warmer for us across the southeastern states. And this jet stream is much more variable, so oftentimes it comes in way to the north. So that subtropical jet A does not bring strong showers and storms to the southern tier, but it also doesn't deflect or thwart the development of tropical systems in the Atlantic Ocean. So La Nina or non-El Nino years, we typically have a more active Atlantic hurricane season. All right, so we talked a little bit about the vertical motion of water in the Atlantic due to wind. We talked a lot about the horizontal motion of water due to wind, the gyres and the ocean currents. Let's talk about how density differences cause water to move. And those density differences create what's called the thermohaline circulation. So thermo being temperature, haline being salt. And what it means is the difference in temperature of the ocean water or the difference in salinity of the ocean water causes different density characteristics of layers of water, which causes the ocean to become density stratified, meaning the densest water will be at the bottom and the least dense water will be at the top. So because of these density differences, there are 5 basic water masses. You have your surface water, central, intermediate, deep water, and then your bottom water. And of course, the densest is going to be the bottom water and the least dense is going to be the surface water. The coldest and saltiest, the bottom water, and the clearest, the least salty, and the warmest, the surface water. So deep water forms and then down wells in polar regions, meaning when water gets up to the polar areas, it gets very, very cold and begins to turn to ice. Well, when ice forms, only the pure water transition has a phase change from liquid to solid. So of all the water in the polar regions that may have salts in it, as that water turns to ice, the salt is left behind, which means the ice forms, leaving behind very cold, very salty water that tends to downwell or sink. So deep water forms in downwells in the polar regions. It becomes Antarctic bottom water or North Atlantic deep water. And this formation and movement of deep water definitely affects the climate. All right, so this global circulation creates a global heat connection. So let's go through this. This is what's known as the Great Global Conveyor Belt. Essentially, the global pattern of deep circulation resembles a vast conveyor belt. That conveyor belt carries surface water to the deep depths, and it does so in the polar regions, and then back up to the surface again in the equatorial regions. So beginning with the formation of that North Atlantic deep water, so that's that water in the North Atlantic that freezes, becomes very salty, what's left over becomes very salty, cold and dense, and sinks, forms that North Atlantic deep water. And that's going to happen again up in the North Atlantic. So that's the water that comes up, it freezes and it sinks, creating this blue arrow here, the North Atlantic deep water, which then flows south under the force of gravity. Water north of Iceland, that's what we're talking about. This water mass then flows south along the Atlantic and then flows over and mixes with the deep water formed near Antarctica. So it flows south and mixes with this deep water near Antarctica. The combined mass, that's the two, the North Atlantic deep water and the Antarctic deep water, bottom water. The combined mass then circumnavigates, goes all the way around Antarctica, and then begins to move north into the Indian Ocean and also in the Pacific basins. Water gradually warms here and mixes upward to be returned to the North Atlantic by surface circulation. So it mixes upward in the Atlantic, flows around that gyre, gets caught up in the southern gyre, maybe flows around South America into the South Atlantic, and eventually up into the North Atlantic. So you start out very cold, you drop to the bottom, you mix with the Antarctic water, you move up in the Indian Ocean, you move over into the Pacific Ocean, you rise back to the surface as you warm, and then eventually you connect back up into the North Atlantic where the whole process starts over again. And the whole very slow moving system, very important for moving heat north and cold back to the south.
It's called the Great Ocean Conveyor, and it's one of the most powerful forces on the planet. It's made up of warm currents which travel at the surface, whilst at the bottom of the ocean are much colder currents. The conveyor transports oxygen, nutrients and warmth around the world. It's vital to the health of all life on Earth. Yet the conveyor wouldn't keep flowing if it wasn't for what happens in the cold northern oceans. This is where the surface water sinks to join the deep water currents. The sinking happens because the water's very cold. This makes it dense and heavy, so it plunges to the bottom of the ocean. And it's this sinking water which keeps the entire conveyor moving. As it travels south, it hugs the ocean floor until it warms at the equator, where it eventually rises to complete the circuit. Without cold water sinking at the poles, the ocean conveyor would collapse. The sea would no longer be supplied with oxygen and nutrients. It would become stagnant and lifeless. It takes roughly 1,000 years for water to circulate all the way around the conveyor. And this global network of currents controls the well-being of the entire planet. Without it, our world simply wouldn't function.
So a couple different illustrations of how the water travels not only across the surface but also over the seabed. At the left, the water layers and deep circulation of the Atlantic Ocean here. So we see where water sinks in the northern parts of the Atlantic Ocean up near Greenland and Iceland as salty water turns to ice, leaving behind very salty, very cold water, which is more dense, and so it sinks. It sinks down at the bottom of the Atlantic Ocean and then flows south until it gets down to about Antarctica, where the same processes cause water to sink in Antarctica. The water turns to ice, leaving behind cold, salty water. It sinks. Those two masses mix. The Antarctic bottom water and the North Atlantic deep water, they mix, and then they travel either over into the Indian Ocean or the Pacific Ocean, and then some upwelling and warming brings them back up to the surface, creating the entire circulation. And so to the right, you have a model of the thermocline circulation caused by heating in the low latitudes. So here you heat the water up, it becomes less dense, and then chilling in the higher latitudes that causes the water to sink. And again, so these differences in both salinity and in temperature create density differences that cause this water to move around the globe, the global conveyor belt. And here's a very simplified view of the thermohaline, both heat and salt, or heat and salinity, temperature and salinity circulation in the Atlantic. Surface water becomes dense and sinks At the north and south polar regions, being denser, Antarctic bottom water slips beneath North Atlantic deep water, and the two kind of mix to some degree there. The water then gradually rises across a very large area in the tropical temperate zones, then flows poleward to repeat the cycle. As it talked about in the text, fresh water arriving in the North Atlantic from rapidly melting polar ice could slow the formation of the North Atlantic deep water, with big implications in the climate of Europe. So what that's telling us is that if the climate warms to a degree that the polar regions see a great deal of ice melt, then all that fresh water that would come from that ice melt would then cause that North Atlantic deep water to form more slowly, because there wouldn't be the density differences. And that could cause some big impacts in terms of chilling the climates of Europe. So that's one of those interesting feedback mechanisms where the warming of the globe may cause the melting of polar ice, but the melting of polar ice actually slowing down the global conveyor belt and therefore cooling Western Europe. In Chapter 8, we've learned that ocean water circulates in currents and that surface currents affect only the uppermost 10% of the world's ocean. The movement of surface currents is powered ultimately by the warmth of the sun, but it's the warmth of the sun and the differential heating of the Earth's surface that causes the winds, and the winds are what effectively cause the ocean currents to begin moving. Water in surface currents tends to flow horizontally, but we also learn that horizontal movement of water along the coastline or near the equator can actually cause a vertical response in water. So horizontal movement of water because of winds can create vertical movements of water. Surface currents also transfer heat from the tropics to the polar regions, and they influence weather and climate. And again, one of the primary ways we see that is with the Gulf Stream transitioning very warm water into the North Atlantic that keeps Western Europe much warmer than it might be at that latitude. The ocean currents also distribute, whether they're horizontal or vertical, distribute nutrients and scatter organisms, and they have also, as we learned in chapters 1 and 2, contributed to the spread of humanity to remote islands, and of course, important factors in maritime commerce. So the other 90% of the ocean water that lies below the surface zone is driven by the force of gravity and density differences in water layers. As dense water sinks and less dense water rises, the world's ocean becomes density stratified. Because density is largely a function of temperature and salinity, the movement of deep water due to density differences is called thermohaline circulation. Currents near the seafloor flow as slow river-like masses in some places, but for the most part, the greatest volumes of deep water creep along through the ocean at the ocean's floor at an almost imperceptible pace. And the Coriolis effect, gravity, and friction shape the direction and the volume of surface currents and the thermohaline circulations. And that does wrap up ocean circulations with an overview of the lecture concepts. We'll see you next time when we continue with the lectures from an introduction to oceanography from Essentials of Oceanography, the Cengage Learning textbook written by Tom Garrison and Robert Ellis. Of course, we're working out of the 8th edition.